All right, I'm gonna open, where's my, this, I suppose. Yes. Okay. Let me go to your class and you tell me, when do you want the deadline to be? Because I uploaded lab 7 today and I thought probably to ask you when you guys are free. So this is the list, lab 0 to 7, 6 is missing. You have the recorded session, you have the lab report ready and the experiment ready. Now let me add the assignment, which is submit here. So I'm gonna call it, yalla, think about the deadline, submit here lab 7, okay? I'm gonna pick a random color just for it to make sense. And the deadline is, I was thinking probably Thursday, 2 days from now. No, it's too early, Friday. Do you think Friday is a good idea? If we discuss it to be midnight. Do you think you can do the lab report by then, or is it too early for you?
Could we take till Saturday?
Yes, of course you can, but I want you, so I'm just checking those grading options, display of grades, where's the display? Show average, always available, and track. Okay, you want Saturday. Keep in mind that today we're doing lab 8, right? And lab 8 is gonna be due next Tuesday, or probably I can delay it a bit. So if I delay lab 6 a lot, lab 7 a lot, lab 8 is gonna be delayed a bit as well. But if you want that, let's do it. Saturday, what do you think, people? Let it be. Personally, I don't mind. I'm gonna take that into account when I put the deadline for lab 8. If some students would like to finish 7 early on and start with 8, remember this is a deadline, and the deadline means, yes, this Saturday. And deadline means submit anytime before Saturday. So you can do it tonight, you can do it Wednesday. So nobody is delaying you. It's only giving some time for the students who may not be able to do it earlier, okay? So may I assume lab 7 is over? Now the issue is, since you did not start reading it, probably you don't have a question about it. Anybody has a question about lab 7? Which means if you would be having questions later on, probably I need to meet with you, and I'm ready for that, or answer some questions via email. So may I assume that all the questions related to lab 7 will be answered via email or WhatsApp or WebEx, since you have no questions now, right? Okay. We can start lab 8. All right, I'm ready for lab 8. Probably we can put the chat next to me because you guys use it a lot, and those away, and probably have a bigger document. All right. Magnetic field. The first time you study magnetic field is in grade 11. That's for the Lebanese curriculum. For the American curriculum, it's a bit different, so it could be grade 11 as well. For the French, I have no idea anymore. All right, Ratib, I'm gonna get back to you in a moment. So I have no idea what they do in the French program. The last time I was in the French program was in 1997. Let me turn off this sound because it bothers me. All right, I'm back to you. Yes, I'm back to you. So I don't know, I will assume you know nothing about magnetic field lines. So Ratib, in your absence, we basically said, where's the plan? We said that I'm gonna discuss the midterm later. I'm gonna send you your confirmed grades, all right? I did not have the time to check them yet because I was very busy with other classes. And we were discussing lab 7 and discussing a deadline for it. Now we're doing lab 8. So magnetic field, you will be given 2 different kinds of coils, all right? Let me explain a bit the difference. This coil, and I'm gonna draw it here. This coil is a long coil. This is an awful one. Okay, so I'm gonna try to be a little bit, yeah. This is a long coil. A long coil is, you have a length, okay, L, and you have a diameter or a radius. I'm gonna call the diameter D. If you compare L and D, D is much smaller than L. And you can see it here. The length is much bigger than the radius. This is the length of the solenoid, and the radius is measured using a regular ruler. All right, I'm gonna call it a long coil, and the long coil is actually called a solenoid. On the other hand, a flat coil is not here, but you have this is a flat coil where the radius is much bigger than the length. It's usually like this. It's flat, you have all the rotations, and then it will go away. All right, this is called a flat coil. It's very similar to a very big bracelet, if you want to say, and you can see it in the video in a moment. So this equation is the magnetic field at the center of the solenoid, okay? Or you can say it's everywhere inside the solenoid. On one condition, the solenoid is infinitely long. Mu0 is the permittivity, the magnetic constant, you can call it. It's 4 pi times 10 to the negative 7, only if you use SI units. N is the number of turns, how many turns you have. In our case, we will take two cases where N is equal to 500 turns, and another L. My internet is glitching, that's why I'm not being able to write well. It could be from the recording. All right, so we're gonna take two cases for N. I is the current, it's gonna be constant throughout part A and B, and L is the length that you can easily measure with a ruler. This is N, okay? Here, for the flat coil, R is the radius, X is the position away from the center, and you're gonna take X to be equal to 0 because you're gonna be asked about the magnetic field only at the center, okay? You will be given a Tesla meter, and the Tesla meter will be measuring the magnetic field inside and outside the coil. Let me show you our x-axis. This is the x-axis. All right. This is the x-axis. You're gonna take 0 to be in this position. If I'm not wrong, this is around 6 centimeters. And this is 8 centimeter long. So probably 6 plus 8 is gonna be 14. And then you're gonna continue up to 20 centimeters. So your probe is gonna navigate from 0 to 20 centimeters. In other words, you will measure what's happening outside the solenoid, what's happening inside the solenoid, and what's happening on the right side of the solenoid, okay? And you will be asked to plot B as a function. Probably I can draw it here. Let me create some space because this is messy in a way. So you will be asked to plot, this is X, right? And this is B. X is 0 again is on the right side. So this is X is 0. So you will have a very small magnetic field. And as you get closer to the center of the solenoid, the magnetic field increases, increases, increases. Probably you will have a plateau. This is only if the coil is really long. If the coil is not long, you will not see a plateau, you will see only a peak. And then it decreases as you go away from the center. And then it goes to 0 as you're really far away from the center of the coil. It's known that the magnetic field at the center is actually very high. So this is the center. Okay? Yes. So,
Doctor?
yes.
Are there any similarities between the magnetic and the electric field?
What do you think? It's a very good question. Probably we can discuss it as a team.
I'm not sure actually.
All right, so let me create some space and discuss it. Electric field, magnetic field, probably create a table. I like this question. I actually like to discuss the difference with the gravitational field. This is so interesting. Thank you for the question. Who was that?
It was me, Ali.
Ali. Magnetic field. All right, who is the source of the electric field? So Joe is saying electric of a charge, magnetic from a magnet. Is it true? So we need a source. So they both need a source. Both need a source. We have the source can be positive or negative, right? Positive / negative. Here the source can be north or south, right? The only difference is I cannot, so N and S cannot be separated, right? In other words, I always have a dipole. I cannot have a monopole. For the electric field, I can separate plus and minus, right? What else? This will induce, all right, this has a direction depending on the source, and this has a direction as well depending on the source. I mean by direction, it could be repulsive and attractive. The gravitational field is only attractive due to the nature of the source. So it has nothing to do with the field. What else? They both travel in vacuum, but it's the same for any field would travel in vacuum, right? What else? They're both inversely proportional to the distance squared, or not? You can answer this question from the course. Concerning conductors, Ratib, can you tell me a bit about conductors? Conductors are for the charge, and you have a current. Like when the charges are in motion, you have a current. There is a relationship. The magnetic field can be created by moving charges, right? Moving charges. The electric field cannot be created by moving magnets, or it can. This is interesting. So the relationship makes it a bit complex to compare both because they're somehow related, you know? Yeah? Anybody would like to add something? Ali, you asked this question because you had something in mind, right?
I did, but I forgot what it was.
So an interesting question could be, and I don't want to give you an answer right now, maybe to give you some time to think about it. Electric field is a function of 1 over d squared. The question is, the magnetic field, is it a function of 1 over d squared or 1 over d? Magnetic field. And the only way to be answer this question is to study Ampere's law and so on and so forth. So this is a question mark. And I know that in the course you did not start this yet. So probably give you a week or two to think about it. And then we can revisit.
I remember now. It's because I was wondering if we can use a method similar to how we use a Gaussian surface to calculate an electric field with magnets.
Yes, you will learn this in the course. And yes, of course, it's called Ampere's law. And Ampere's law is a bit different than the Gauss's law. And I think your teacher is going to compare both laws, all right? So the Gauss's law actually deals with the fact that you have an integral and it's equal to epsilon 0 over q inside, right? Or q inside over epsilon 0. The magnetic field, the Ampere's law, you will have current inside mu 0 over current. So instead of epsilon 0, you use mu 0. And instead of charge, you use current. And it's very, very similar. So yes, there is a law for that, okay? I would love to discuss the difference with you after you start with the course. I have a table that actually would show you a nice similarities and differences. Okay, so let's come back to this. Next week, I'm gonna say, do you have questions about Lab 8? And probably discuss this more. And thank you so much for your question. Let me color this so we can keep it somehow, somewhere. All right, next. All right, so I wanted to discuss the dynamics of the lab. I wanted to tell you that you had part A. Okay, so this is part A, in which you have case 1 and case 2. This is part B, in which you have linear regression and error on the slope. This is something that you already know, but you're still not great at it. Electric field doesn't move the charges, the magnetic field does. Of course, the electric field will make the charge move. You have the electric force. And yes, you have the magnetic force, the famous magnetic force that makes a wire to move. I think this topic is really big and it will be extensively discussed in the course. Probably if you want, we can have a review session later on for the course, just to be a backup review if you want. This is a very interesting topic, and of course you will have wires moving, and that's so crazy. And then part C is you're gonna study the flat coil. So this is solenoid again, and this is flat coil. Here you will take solenoid 1 and solenoid 2. The only difference is N. It's wrong to say the effect of the length. They mean the effect of the position. You will measure the magnetic field at different position, at position 0, 1, 2, 3, and so on and so forth. So it's not the length, it's a different position. You will have to repeat the same procedure for a second solenoid where you have N is equal to 1000. So you will have exactly the same plot, but probably bigger or smaller, and you're gonna discuss the differences and the similarities between both plots. So probably you can discuss the shape, you can discuss the values, you can discuss the center, because you know the center from the different measurements, and you can see the center on the graph. I'm gonna show you the lab report in a moment. So you can discuss the position of the center graphically and in real life because you took the measurements of the length, and you're gonna compare both. So effect of current, you will set the probe at the center, and this is a constant, and you will change the current from 0 to 1 ampere. Since B is equal to mu 0 and I, have you ever saw this equation before? I know you are the COVID-19 generation, and probably not everybody did. So this is the magnetic field at the center of the coil, of the solenoid. Since you will be varying the current and you will be measuring the magnetic field, mu is constant, N is constant. You will pick one solenoid and you will not change it. The length is constant. If you plot B versus I, you get a straight line passing through the origin. I need somebody to tell me what does the slope represent. If I plot B versus I.
The constant mu 0 times N over L.
Thank you so much. Is that Ludovic?
Yes, doctor.
Yeah. All right. So the question is, just a second. I need to know what does the slope represent. And this is where Ludovic, your friend, said that the slope is actually, let me just move out of the box. The slope is actually this guy. All right. So you're gonna say slope is equal to mu 0 N over L. Now you can find N by stating it's the slope times L divided by mu 0. I know that somehow I'm solving your lab reports, and I think it's okay because this is recorded and you can watch the recording again to be helped throughout the lab reports. I want you to do that. Do you guys know how to find the error on the slope? I think you should know by now, right? And once you find the error on the slope, I need somebody to tell me, how do I find the error on N? Let me write what Ludovic just said. So,
I'm using linear regression.
yeah.
Since we know that L is measured by a rule.
Yes. So can you tell me again what N is equal to? If we're saying that slope is mu 0 times N over L, so what would be N equal to?
The slope times L all over mu 0.
So slope times L divided by, so this is big L divided by mu 0. All right, which means you have to do the derivative with respect to the slope, then derivative with respect to L. You don't do the derivative with respect to mu 0 because mu 0 is a constant. The error on the slope, you need to measure it, to calculate it. The error on L, you're using a regular ruler. What is the error on L for a regular ruler? Alpha L, what is it equal to? For a regular ruler, who knows?
0.05
Yes.
centimeter.
Thank you for saying centimeter. This is something that everybody knows by now. All right. So you do the derivative with respect to the slope times alpha slope derivative. All right. And a lot of students still don't know that all the errors must be how many sig figs?
1.
Yeah, must be rounded to one significant figure. This is important. A few hours before the midterm, I was correcting some work and I realized that a lot of students still have difficulties with this. Okay? All right. Now for the flat coil investigation, you're gonna repeat. Let me move this a bit. All right. For the coil investigation, you have a flat coil. I know that this will make more sense when you see the video. You're gonna repeat exactly the same experiment you did inside the solenoid, but you will do it for a flat coil. Let me draw a bit for you to see where exactly, and let me move this a bit. So this is your flat coil, okay, flat coil. I need to show you the x-axis. You will measure the thickness, the radius, anything you want. This is your x-axis. Okay, you're gonna take 0 to be at the center. This is 0, and you're gonna take positive 5. So 1, 2, 3, 4, 5 to be on one side of the solenoid. We're talking 5 centimeters, and then 1, 2, 3, 4, negative 5 to be on the left side of the solenoid. And you're gonna move the probe as you go away, so at each and every position. Okay, now when I show you the video, I need to discuss a bit the errors on different values, because now you need to see the equipment needed. All right, so let me show you a bit the lab report. Average diameter of the solenoid. The solenoid is actually very thick. So this is the solenoid, right? It looks like this. And you will see wires around this. The view from the side, a cross-sectional view, will look like this. In other words, this is so thick. All right, let me just, so this is basically very thick. You will be asked and you will be given the outer diameter and the inner diameter. And when they say average diameter, they don't mean average, they mean the middle diameter. In other words, if I take this circle into account, what would be the diameter of the mid circle? Do you have an idea how to do that? So it's the mid diameter. How do you find the mid diameter if you are given the outer diameter and the inner diameter? Any idea? Yes?
The inner one and the bigger one, and then we divide by 2.
Exactly. I take the outer plus the inner and I divide by 2. So again, this is not an average. It's a simple diameter that is the mid circle, okay? Because average, remember, to define average, we have to repeat exactly the same measurements over many trials to find the average. You don't actually do two different ideas and you average them out. This is called median and not real average, but we say average sometimes. It's just using the English language. Now the length will be given to you, the number of turns given to you. Then I'm gonna move, again, this is confusing a bit. X is equal to 0. You go back to this diagram. So 0 means outside the solenoid, because last semester we took this to be 0 and this to be -6. It was also confusing. So you just need your axis to be visible, that's all. I'm gonna give you the magnetic field at all the positions. Now your job is to plot. May I assume everybody here in this room knows how to plot using Excel? And then they ask you to find the position of the center of the solenoid. So it's basically where the peak is. Okay? Comment, you will say that knowing the length of the solenoid, the center should be, let's say, at position, I don't know, 8 centimeters. And you got probably 7 centimeters on the graph. You do the percentage difference, you say accurate or not, and you list the sources of errors. Okay? Then for the part 2 I'm still in the same part A, but this is solenoid number 2. The average diameter is gonna be the same, the length the same, the number of turns is gonna be different. I think n equals 500 for the first one, n equals 1000 for the second one. I'm gonna give you the values. You're gonna plot on the same graph. Take some time to see how to plot two different plots on the same graph, and then they want you to compare. So again, think about what's similar and what's different, and try to come up with something proportional to something. Don't just say this is bigger, try to say proportional or not. And to prove proportionality, try to find a constant ratio. So B1 over B2 is equal to constant, something like that. What can you conclude? You come up with a conclusion, probably related to linear or not. Think about it. While you do the lab report and you're watching the recording, probably you would know what I'm talking about. Now I'm gonna pick one solenoid. I don't know which. It will be given to you. Same average, same length. The number of turns probably is 500 or 1000. I must tell you, I'm gonna vary the current and measure the magnetic field. Be careful, this is at the center only. So this is at the center. So this is being delayed because of the recording. And then you're gonna plot, and you're gonna get a straight line passing through the origin, and you're gonna find the slope using linear regression on Excel. Please let me know, meet with me if you don't know how to do it. I can help you with it. Don't wait. Don't let your partner do it until you don't know how to do it. The final exam, probably you will have to submit some lab report, not only multiple choice. Two functions on the same graph for the first part. Yes, for the first part and second part, you do it both on the same graph. If God forbid you don't know how to do it, you will plot each alone, but this will not really be good for you because you won't be able to plot both. Excel is gonna change the scale for you. So try to do it on the same graph. It's very easy. You don't know, YouTube it, it's easy. And then you're gonna find the uncertainty on the slope. This will take you some time. You don't know, it's time for you to learn. Today is your time for you to learn. Don't wait until the final exam. Yes. Compare the slope. From the slope, find the number of turns. I already helped you with that, and Ludovic was my n side. And the uncertainty on n. Compare to the theoretical value. You already have n to be equal to something. I don't know, 500 or 1000. And the slope is going to give you a value that would be really close. When they ask you to compare, what do you do? Anyone? How do you compare two values? Do you say bigger, smaller, close, away? How do you compare two values?
We find the percentage error.
Yes, let's call it percentage difference. Yes, and when they ask you to comment, yeah, and when they ask you to comment, what do you do?
We cite the sources of error.
Yes, if you believe the same sources of errors are happening all the time, you can simply say the sources of errors are listed above. And try to add one idea because the setup is changing between each and every part. All right? For you to really get an idea what the sources of errors are, now as we're watching the video, probably I can go over some. For the flat coil, you're gonna be given the number of turns, the average diameter. Probably you don't need this, or Bala, you need it. And the current is gonna be constant. By the way, the current is constant throughout the whole lab except this part. Okay, and I'm gonna vary position -5 to position plus. I made sure this is too significant, 2 decimals because of the error on the regular ruler. I'm gonna discuss the error on B when I show you the device in the video. Then they want you to compare the value of the magnetic field at the center. This is the center here. This is the experimental value and the theoretical value taken from the equation. Compare means percentage difference. Comment means this is sources of errors. And that's it. It's not a long lab. It's only that this part is long, 6 and 7. Please, everything must be typed. Now you are 2 partners doing 1 lab report. Some students do not have a partner yet. It's okay. Probably it's better for you. Then you have to study less for the final exam because you will be doing the hard work during the lab reports. But again, you can find a partner if you want. I can be your partner. I can help you. You just have to meet with me once and we can do it together. and make sure you type everything, okay? You just have to type one equation and then copy paste, modify the equations. You're gonna learn to make it fast. I think I'm ready to go to the video. Yeah, so I have it ready. I missed the lab. I did not visit LAU for 3 weeks now. Okay, so this is the flat coil. You can see 2 flat coils. I'm gonna use only one. These are the solenoids. You see they're long, but not too long. And they have a cross-sectional that looks like a square. This is the Tesla meter. It's a big device. It has a big probe, like a ruler. The tip of the probe is gonna do the measurement. It's a digital measuring tool. You can see a screen. You have an ammeter to measure the current and to make sure it's constant. Let me show you what I was doing. So again, I'm not, all right. This is me showing you the probe. This is the probe. I'm gonna move everything away. I'm gonna show you, this is the ammeter. It's digital. Smallest subdivision is the error. These are the wires. And this is the solenoid. I'm explaining what's on it. Let me, N is equal to 500 turns. L is the inductance. You can ignore it for the moment. R is the resistance of it, and the maximum current allowed is 2.5 amperes, above which it will heat up. So we don't want to go above 2.5 amperes. And by the way, 2.5 amperes is a lot. Usually we work up to 100 milliamperes, 200, or anything below 1 ampere is safer to deal with. All right, so I think the current is gonna be 1 ampere throughout the experiment. Unless, you know, we need to vary the current, we're gonna vary it from 0 to 1. So we don't want our solenoids and flat coils to heat up. Remember, they're basically wires coiled around something, so they heat up, you know. Yes, I'm gonna show you the connections. So I'm explaining the outer and the inner diameter in here. Okay, outer, you see it's really thick. So I'm explaining this is solenoid 2, it's red. So N is 1000, this is the difference. Now this is the flat coil. I'm showing you that the flat coil has a big radius and a small length. I'm showing you the ruler, it's a regular ruler. Now I changed the position of my camera to do the connections. It's an ammeter, so I'm explaining the ammeter should be connected in series. So I need to create a triangle because series connection is confusing to some students. So I need 1, 2, 3 wires. Okay, I'm gonna connect with 3 wires. We see blue, yellow, and red. I'm gonna keep this. Sometimes when I'm outside of the camera, don't laugh at me because my phone is not working in selfie mode, so I don't know what I'm filming. That's why I go out of the scope. Otherwise, you cannot hear me. It has a sound problem. So I'm turning my power supply on. I'm fixing the current to 1 ampere, I think. And here, the solenoid is lying on the desk. I'm gonna show you how the tip of the probe is doing the measurement. I'm showing you also how I zero the instrument. I put the probe inside the solenoid and I switch off the current. This should give me 0, and it's not, because I have a lot of magnetic noise around me. The Earth's magnetic field, the Wi-Fi magnetic field, they have a resistance, but we neglect it. Yes, the resistance of the solenoid is neglected. It's not very small though, and that's why it heats up. All right, so do we neglect it? We don't actually mind it. Since we're measuring the current using an ammeter, it's like we're taking into account the resistance of the solenoid. All right, so I'm saying we have magnetic noise. It's due to the Earth's magnetic field, to the Wi-Fi around you, to my cell phone, to the network. Usually, if we have many benches functioning, they give magnetic field to each other. Like your neighboring bench will affect your magnetic field. So there's a 0 knob in here, just above the green spot. And I can zero my device before I start. So 0 current should give me 0 magnetic field. And then I switch on. So this is here, I'm zeroing my, you see the 0. I'm showing you millitesla and two decimals versus 3 decimals, just to show you the precision of the measuring tool and therefore the error. And then I'm turning on my power supply, and here I'm gonna move the probe to different positions. and show you how I actually measure the magnetic field and how the magnetic field increases and decreases as I change the position of the tip of the probe. And then I said I'm gonna change the solenoid to the red one. Yes, not the yellow one. Do exactly the same procedure. And then here, I'm gonna keep the Tesla meter in the middle, and I'm gonna change the current. And you can see the screen of my ammeter. I'm gonna change it from 0, 0.1, 0.2, 0.3. And as I vary the current, I read the magnetic field. Digital, digital. So you can see how many decimals, and you can learn about the error on your measurements if needed. And you will plot eventually. So you see 0.1 and so on. I'm gonna give you the values. Right, eventually there's a section about the flat coil. So I'm discussing here there. This is the flat coil. It's exactly the same connection. And there's a way to fix my probe. I'm not gonna move my probe inside and outside. Instead, I'm gonna move the solenoid because experimentally it's easier. Also, the solenoid has a special ruler, and I'm gonna move the chair a bit so you can see the ruler. I'm moving the solenoid in and out. I move the chair to show you the red arrow and the regular ruler in here so I can tell if I'm moving the solenoid 1 centimeter at a time or not. Okay, you see? This, not the solenoid, the flat coil. This flat coil I'm not using, and this one is not connected, so there's no current in it, and it creates no magnetic field at all. So just ignore it, but I cannot remove it out of my bench. It's glued actually. This one can move, this one cannot move. So I'm doing the experiment only on one. Do you have an idea why I do have 2 flat coils attached to one board? Have you ever studied in high school 2 different flat coils like that? They have a special name. I remember there's a section in the Lebanese book in grade 11 about that. 2 flat coils facing each other. Something like 2 parallel plates facing each other. Does it ring a bell?
Capacitor.
Capacitor. What's interesting between the plates of the capacitor? What's happening in between the plates? Something interesting.
An electric field.
Yeah, what's interesting about the electric field between the plates of a capacitor? Uniform. Thank you, Ludovic. Yes, it's an electric field that is uniform. Now, if I have 2 flat cores facing each other, what I can see in between is the magnetic field B1 plus B2, the resultant. And have you ever studied a case where the magnetic field is uniform? Probably not, but have you ever studied this case? 2 flat cores facing each other. My sound is lagging. Let me turn off the camera a bit. Yes. So let me say it again. 2 flat coils facing each other and the magnetic field between them is uniform. Any example you can remember from high school? 2 flat coils, they have a special name that starts with H. You know? Helmholtz coils. Have you ever heard of Helmholtz coils? You don't know Helmholtz coils. So what's interesting about Helmholtz coils is if you take the distance between the flat coils to be exactly equal to the radius of the coils and make sure you connect them in series, same current, same direction of the current, the magnetic field between the flat coils will be B1 plus B2, but as you move between the flat coils, B1 decreases, B2 increases at the same rate, the resultant is gonna be uniform. And scientists believe to create a uniform magnetic field in a certain region is very interesting. And this can be used a lot for research, especially in biology. You can probably grow a plant between them or do an experiment between them. The magnetic field is uniform. This is very interesting. That's why actually we have this board, because we use it for Helmholtz coils. Now we're not doing any Helmholtz coils, so I need only 1 flat coil. I'm gonna ignore the other one. And no, it's not connected to the current. So it's acting like a plastic bracelet, if you want to call it, where there's no current and no magnetic field. All right? I think that's it. Is that it? Yeah, I think that's it. This is a very interesting experiment. I know, too bad you're not being able to do the experiment yourself, especially your class. I know your class is the class that is the mostly interested with those experiments. I tried for us to go to the lab. It's very difficult. I'm so sorry for that. Hopefully next spring you can be on the campus, because eventually you have a lot of electronics related lab and you need that. That's it for me. So I'm gonna stay in case you have questions. I know that our session is not enough. Please make sure you watch the recording again and the video slowly of the experiment. The recording will help you throughout your lab report. Try to meet with me anytime you want. I'm ready to meet with each and everyone separately. And remember, if you're not meeting with me, your friends are. So which means what I can offer this luxury for everyone. That's why I don't have real office hours. Although you can see them in the syllabus, I don't want to stick to them. Every day and every hour can be office hour, okay? Please use it. Use it, just let me know, okay?